Hello, can you hear me?
Yeah.
Okay. So, okay. Mm, So let's wait a couple of minutes, then we'll start. Okay. Can you see my screen?
Yes.
Okay. So, still we are covering some of the basics of antenna or related to antenna. Um, so now today we are talking about field regions. So antenna's behavior is not same in at every distance. It changes. So what is field region? Um, so if this is an antenna, and so the first region around this is called reactive near field region. Okay. And reactive near field region is actually where the things are starting to happen. So it's highly reactive region. There is mutual coupling as well, and it's not properly radiating, started radiating, and the electric field and magnetic field components are not exactly in the perpendicular. So it's just things are starting to happen in this region. How you define that this region exists? So it's like a rule of thumb, they say, that if your distance from R is um, like distance from antenna is less than 0.62 d cubed by lambda. So what is d? D is the dimension of antenna. So if it is less than this distance, then it is in the near field, reactive near field region. Now, if you think about this one, so this is a region where electric and magnetic field coming started to come in perpendicular, or they are trying to propagate in phase. So what is that they are trying to propagate in phase? We will talk about it. And another thing we are talking about here is they are not displaying spherical wave front right now. What it is, we will also talk about that. But this is the near field, what you should say, region. So both of them are. So what is the measurements normally we take are in the far field region. So because antenna is designed to operate in the far field region. And far field region is when you have your distance r is greater than 2d square over lambda, where d is the dimension of antenna, lambda is the wavelength. So whenever your distance is greater than this quantity, you say that you are in the far field region. In the far field region, there is a spherical wavefront. There is a electric and magnetic fields are in phase, they propagate in phase, so it's proper action of an antenna. So another thing in the that differs in the far field region and the near field region is that in the near field region there is much of the stored energy, but in the far field region it converts into the radiating energy or the real energy that radiates. So I mean, these are little vague terms right now, but it will become clearer, more clearer. Right now, we are just introducing that there are some regions in antenna where antenna does not behave the same. So after 2D square lambda, it's all far field. It's okay, it's good. But within, if, so another important thing is, as these regions are dependent on wavelength, so if your antenna is bigger than wavelength, wavelength is like the frequency at which it is operating. So if your antenna is bigger than wavelength, then its regions sizes would be different than if your antenna is smaller than the wavelength. Do you understand this? Right? Because we are comparing it with the wavelength here. So it is dependent on the design frequency at which it is designed. So if antenna is bigger than the wavelength, so if your D is greater than your wavelength, then it just depends on your D. But if your lambda is bigger, then your radius will be, then the lambda contribution will come. So that's what I'm trying to say, that if your antenna size changes, the region sizes will also be changed. Okay. Any question about this? Okay, let's talk about what is spherical wavefront. And I saw some of the comments in which you are saying that there is still some confusion about the lobes. We will come back on that too. But first we will cover this, okay? So what is spherical wavefront? Like here you are seeing here that I'm saying that fields exhibit spherical wavefront. So what is spherical wavefront? I just want to discuss that. So what is wavefront? Wavefront is when you have a time varying field and your field try to propagate itself, right? But it will propagate in such a way that your all points will support that. So if this is your point source, these are the like the direction of the fields, and they're all in the same direction to support this to propagate. And similarly here, this is a plane wavefront in which all of the fields are supporting it to propagate, okay? So if you see here, so this is the Huygens principle in which they say that each wavefront is the envelope of the wavelet. Each point on a wavefront acts as an independent source to generate another wavelet for the next wavefront, but they work together so that the wave propagates in phase. So that's what the wavefront is. Wavefront is the collection of the points that are working together. Okay? Parker, do you think it's fine?
Yeah, that makes sense.
Okay, so what I'm talking about is, this is a plane wavefront. In the plane wavefront, all points are moving in the plane, right? So if you see, this is a wave that has the plane wavefront. And similarly, if I'm just drawing the wavefront, this is a wavefront that is propagated in this direction. So it's propagating in the plane wave like that, right? So if I just say what is spherical wavefront? So a spherical wavefront, it is different from plane wavefront, because in spherical wavefront, you think that energy flows in all the directions, and it acts like that it is moving in the sphere. You have a spherical waveforms, okay? But it also happens that after a certain time, if your source is too far, your spherical wavefront becomes the plane wavefront too. But in the spherical wavefront, you can see that energy of the wave is carried away equally in all the direction in the sphere. Okay, is it clear? So what we are saying that in far field, antenna radiates in spherical wavefronts, right? But in near field, it's just try to like warm up itself and does not act as a spherical wavefront. So this is another example in which your plane wavefront is changing into the spherical wavefront. So because you have an obstacle in the way of plane wavefront, and there is a small slit, so it acts like that there is a point source that's making it a spherical wavefront. Yes, Andrew?
So would you be able to use a triple integral to figure out the area underneath the curve
Of?
in a three-dimensional spherical wave?
Yeah, we will come to that. Yes. Today we will touch a little bit about it. Okay, Andrew?
Yes, thank you.
Okay. Yeah, so that's the spherical wavefront, right? We little bit touched upon on the spherical coordinates, but we did not do the integrals yet, but we will come to that. Okay. So are we clear about this? Okay. So now we know what is wavefront, what is spherical wavefront, what is plane wavefront. Now we can visualize that how far field is behaving. So if you see, this is an antenna, this is a radiative or reactive region, this is a Fresnel region, and this is a far field region. So far field region is also called as Fraunhofer region, okay? It's based upon the scientist who found it or who discovered that. So that's what I am trying to say, that so electric and magnetic fields are trying to warm up themselves. They are not exactly in perpendicular, or their points are not exactly in phase, so that they can act as a spherical wavefront, okay, until they come to the far field. Similarly here, if we see, this is another point of looking at in terms of the field lines. So you can see that field lines are starting to act as that they are supporting each other to become the spherical wavefront. So is it easy to visualize now? The difference between the regions?
Yes.
Okay. So now there are some pattern types we want to discuss, okay? So this is the pattern of isotropic radiator, which is an imagination. In the world, there is no isotropic radiator, okay? So it's just a hypothetical, like the imagination or lossless antenna, which radiates equally in all directions. So that's called an isotropic radiator. So we think that there is a radiator that equally radiate in all directions. It is ideal, not physically realizable. It is often taken as a reference for expressing the direction. So yes, why we define isotropic radiator? Because we define all the quantities with respect to isotropic radiator, because it's like a unit one or reference one, okay? So that's what our isotropic radiation pattern is, okay? Then that's what we were doing in the design block yesterday. There is this radiation pattern that is called dipole. So that is the radiation pattern of dipole, but this radiation pattern is called omnidirectional radiation pattern. So in omnidirectional radiation pattern, you can say it's a donut shape. Donut shape means that it's acting as that it is transmitting energy in all the direction of the phi, but not in the direction of theta, right? So it's near to omnidirectional, but it's not omnidirectional. Oh, it's near to isotropic, but it's not isotropic. It's an omnidirectional pattern. It's a special type of directional pattern in which you are seeing that it is radiating in all direction in one plane, but not in the other plane, right? So it's not radiating here, but it's radiating here. What is azimuth plane? We will talk about it. What is this thing? We will also talk about it. So you don't have to worry right now. Okay. So now there is another type, which is called directional pattern. So directional pattern is in which you target, like we were talking about before, in which you are target one, not one, maybe set of the frequencies, but you are specifically target one direction. So it's not omnidirectional that sends energy in the plane in all direction, but it specifically targets certain direction, right? So that's called the directional pattern. And it's normally its directivity is not is greater than the omnidirectional pattern, but that's just like the introduction of this directional pattern. Okay, now I want to introduce some of the terms that we have used before and we may not know. So I told that I showed you 3D patterns, but in antenna we all the time talk about 2Ds. We showed that how there is a phi cut, how there is a theta cut. So because it's important to see the details of the patterns, okay? So these cuts or 2D planes are called principal plane patterns. So we will talk about this. Okay. So what is azimuth plan or elevation plane, sorry. 1 minute,
Professor,
yes, go ahead.
they're using gyroscopes, so northwest, like 3-dimensional direction.
Okay. What you're saying, I just didn't get it. What you're saying?
I was saying that azimuth is usually something that you refer to as a directional based propagation.
Yes, that's what I'm saying. Yeah. Yes, I'm explaining what is azimuth and what is elevation.
Oh,
okay.
I were asking. I'm sorry.
Yes. Oh, okay. What I'm saying is that it is used in the, I think, astronomy a lot of times. And whenever they are, many people, I think in many fields, they use this lay term like azimuth and elevation. And we also use it in antennas. Okay. So what is azimuth? Azimuth is opposite to the, what you should say, elevation, of course. But azimuth is the horizontal. It means horizontal. And elevation means vertical. Okay. And if we see this thing, so let's say antenna is mounted somewhere and we are measuring direction with respect to that antenna. And we are saying that this horizontal plane is the azimuth plane and this vertical plane is the elevation plane, okay? And another way of looking at it is that you think if you are seeing the rectangular coordinate, this is your rectangular coordinate, your XY plane is azimuth plane, right? Kate?
Yep, I understand.
You got it? Is it too fast?
Yes. No, I think this is a good pace.
Okay. So what I'm
Can
saying
you hear
is,
me?
yes, I can hear you.
All right.
Yes, thank you. So what I was saying is that if you display your pattern in XY plane, it's azimuth plane. And if you are doing it in the no, not Y, it's XY plane is the azimuth plane. And if you are doing it in the XZ plane, I think it should be, right? If you think about it, for this one, it's I think XZ plane. But if you have here Y, then it will be YZ plane. Okay, but it's just the vertical plane. Okay, and another thing is if you try to visualize your antenna like that, I'll just show you this thing. So I think we did it many times before, but this is my 3D pattern, right? And if I just cut the horizontal, what you should say cut, it will appear like this, right? If I just did horizontal cut, like here in this plane, if I cut it, okay? So it will be the horizontal plane. So that will be what? Azimuth or elevation? What do you think? Sarah, what do you think what it is? This one, is it azimuth as elevation?
It's azimuth.
Yes, is azimuth, right? And of course, this would be the elevation because it's cutting it from the vertical plane, right? We are clear about this? Josh, are we clear about this?
Yeah, I think this makes sense.
Okay.
Well,
Now,
I have a question about that.
yes,
Sorry.
go ahead, go ahead.
So there were two separate vertical cuts. Are those both like elevation planes?
Yes.
Okay, thank you.
Yes. Yes. Another way of describing the plane is another way of describing it. So you will see all sorts of names in the planes. That's why we want to describe them all the time. So there is another way of describing them is saying that this is E plane or H plane. Okay. So we are not going in too much of this detail, but we are actually trying to imagine ourselves. So let's say this is our omnidirectional pattern of dipole. And we know that this direction, let's say, we know that this direction is the direction of electric field, and this direction is the direction of magnetic field. So we will say that the plane containing maximum direction of electric field is the E plane, and the plane containing maximum direction of H field is the H plane. So now if you compare it with elevation and azimuth, it also makes sense with that. I think H plane should be your azimuth plane, right? Right? So H plane for this particular dipole case is azimuth plane because it's the horizontal plane, and E plane is the vertical plane. So in the case of dipole, these planes are same, but they may or may not be same in all cases, because may or may not be your E field direction is in the direction of azimuth. No, sorry, in the direction of elevation. So based upon the direction of the vectors, your planes can change. But in dipole, azimuth is equal to H plane and elevation is equal to E plane. Okay? So if we try to look at another time, another way, so it's the same that we were talking about before, that this is the horizontal cut, which is equal to H plane, and this is the vertical cut that is equal to the E plane. And if I am just saying in terms of 3D, it's also acting like this. So are we clear about this?
The green diagram is the H plane, right?
So the green diagram, the light green thing is your H plane. The dark green thing is your E plane.
Okay, that makes sense.
Okay? So are we clear about the planes?
Yes.
Okay. Ria, what do you think? Is it fine?
Yes.
Okay. Okay, so this is the fun part, actually, I think. So another thing I want to talk about is radian and steradian. Okay. So the radian, what is radian? So in one dimensional thing, when you talk about radian, you say that measure of a plane angle is a radian. Or 1 radian is defined as if you have a circle and this is your, like you are making an angle with an arc. This is your arc. Then radian, 1 radian is equal, or you can just define that this is your length of arc, S is equals to R theta, where R is the radius of this circle. Maybe I should do this like that, 1 minute. Okay, let me. So can you see this?
Yeah.
Okay, so what I was saying is that what is radian and steradian? Okay, so radian is, if I am having a circle and I'm extending and this angle theta, and this is R, this is S, this is R, then my S is equal to R theta, right? And in this case, if somehow if this is unit circle and my S is equals to R, then my theta will be equal to 1 radian. Okay. And other thing is that if I say, in this case, S is equal to R and theta varies from 0 to 2 pi, right? D theta. So it will become S is equals to 2 pi R. Right? And if S is equal to 2 pi R, and if I say that for a unit circle, R is 1, S is 1, then what will happen? That this will become as like the total circle, it have the 2 pi radians in it. Which is true. So in 1D, you can say that when there is an angle in the circle that is extended on an arc, it is equals to S is equals to R theta, right? And so now if you go back, so is it clear or is it fast?
It's clear.
Because we have covered it before, right? Somewhere you must have done this radian thing.
Everywhere.
Okay, so Bryce, what do you think? It's fine?
Yeah, I think it's good. I'm picking up.
Okay, so let's go back, okay? And we want to talk about this. That's what we are talking about this here. Okay, so what we were saying here is that our radians will be 2 pi. If we are saying circumference of the circle of the radius is 2 pi r, then there are 2 pi radians. Otherwise, in circle, you are saying that this angle is equal to 1 radian if it is a unit circle, okay? But it's different from steradian. What is steradian is, it's actually the solid angle, not the angle that you subtend on the arc. It's like the angle that you subtend on the sphere, right? So this solid angle is very, very important for us because we all the time deals in terms of radiation patterns. So if we talk about this solid angle, okay, so you can see that solid angle will not complete until we have 2 sets of radiuses instead of 1, right? Here we will have just in the 1D, right? But here we have 2 things, okay? And what are these? We will see that too. But first we need to understand that we want to find out a solid angle. So if you go here, just forget about the volume element, or I can just little bit, 1 minute. I can go back actually and talk about this 1 minute. Maybe we have here or not. Just a minute, Andrew, I'll come to you. So when we were saying, or before that, when we were saying r sine theta, where is that? So this one. So if you see, this was our r sine theta, right? And this was our r, right? So what I'm trying to say, if they both work together here, right? Then we are saying that the angle that is made between both of them, like if you are making a circle due to these both, then it will be a solid angle. Okay, so if you think about this, or let's come back to that scenario again. So here you can see that this is your R, but this is the image of your R sine theta. This R sine theta has this image here, okay? To see that this is making a solid angle here, if this is a circle here, okay? So let me again make it clear. Have you done steradians before? Okay, okay, it's fine. Just a minute. So again, coming back, I want to just show you what it is. But now if you see what I'm trying to say, so if this was my R in the spherical coordinate, and this was my R sine theta, or which was making an angle phi, if I subtend that or make the image of that, and I'm saying that, or you can also say that 1 minute. You can also move this one up and say that if I make some angle like this here, that will be my solid angle. That is making with the R sine theta and R with the help of them. Okay. Yes, Andrew, go ahead.
I think you kind of touched on it, but the phi was what my question was about. When you put the multi-dimensions in, you create the angle about the z-axis.
Yes, that's what
And
we,
you were
yes.
getting when you asked what steradian is.
Yeah. Yeah, so what that, yeah, I want you all to visualize is in terms of 3Ds, right? So that's what I was trying to do here, that how we will do that. Okay. So that's what I was saying. So this was R sine theta multiplied by R. So if you pay attention on this, you are saying that, so if I'm saying that if I want to measure the area here, dA, it will be the change in d theta and d phi, right? Because if this area is changing, so I am changing d theta and d phi both. But it's just not d theta and d phi. I want to tell what I am talking about. Like here I told S is equal to R d theta, right? So here I am writing dA, or here I should say ds, right? So here I am saying dA is equal to R d theta and R sine theta d phi. Is it clear? Cedric, what do you think? Is it not clear?
were you talking to me, Professor?
No, Cedric. Noel,
Oh, I think it's clear. It's fine.
it's fine. Do you have any question?
Not at the moment.
Fabian, what do you think?
Oh, looks good. I think you could definitely like simplify it, right, with 2 R's and make it just R
Yes,
squared.
yes, that's what, yeah. But I'm just trying to tell that from where our sine theta comes, it comes with the change in phi, and r d theta comes with change in theta, right?
Okay. Yeah, that makes a lot more sense.
Okay. So now if you simplify them, it's just r square sine theta d phi, and that will make your dA. But solid angle does not have r in it, unit r in it. So they said that solid angle has dA by r square. So this is the formula of your solid angle. And if you see, you can say that your solid angle's maximum variations are from 0 to pi and 0 to 2 pi. Right? Is it fine? Why from 0 to pi in terms of theta? Louis, what do you think? Why we are saying that maximum variation is 0 to pi in terms of theta?
Can you say that one more time?
Why we are saying that maximum change in theta should be 0 to pi?
Because that's the is that the total like area of it? Or
Yeah, that's the total available change for
Yeah.
us. So if this is your theta, right? You can only change from here to here.
right.
Here to here, it will be the repetition. Right?
Yeah, so I said 0 to pi.
Yes, that's why I'm saying that
Oh.
theta can all be changed from 0 to pi.
Mhm.
Right?
Right.
Okay, and when you say phi can be changed 0 to 2 pi, why not it's only changing from 0 to pi?
Because
Yeah.
phi is from 0 like to 2 pi for that.
Yes, 0, because
area.
phi varies in the circle, right?
Yes. Yes.
Okay, so we are good about steradians?
Professor?
Yes,
Professor,
yes, yes.
a quick question. Can
Yeah.
you compare the range for theta to the E plane and the range for phi to the H plane? Or
Yeah,
is
yeah,
that a
that's,
stretch?
no, that's good. So if you see here,
Okay.
this one, so this is your E plane. It's the same as what we are talking about. So this is changing E plane maximum limited from 0 to pi, right? And H plane can change in 0 to 2 pi. Right? That's what you're saying?
Yes.
Yeah, it's very, very relatable to E and H plane. That's the right thinking. So because it's all in terms of theta and phi, it's just the different names. Okay? Some say it's azimuth plane, some say it's E plane, but it's all in terms of theta and phi. Okay? So I was just saying steradians and radians. I want to make sure that you know that. So we are doing this question now, which is in your book, I think first example, in which they are saying we have to find a solid angle, okay? So one question, the question is to find the solid angle using the formula that we have derived. And then another question is to find a solid angle using the approximation formula. So what I was thinking about, what is this approximation formula? I never saw that and stuff like that. Then I searched for it, then they are talking about, say they are talking about spherical cap on the North Pole region. So it's some approximation that people use for the astronomy, okay? So this is some approximation of solid angle the people use for the astronomy when they do the North Pole, when they're trying to find the difference in angles in the North Pole of the Earth. So what they do is, if you have something like this, so think about that this is an Earth, and they want to know this angle separation. So they say that it will be just the multiple of del theta, which we are doing here. So we should not put too much of our energy here. But in astronomy, they say that solid angle is just a multiplication of two perpendicular angular separations. Okay, so we need to compare both of them. So let's see. Okay. Okay, I will be doing this. So what was the question? Question was, for sphere of radius r, find solid angle of a spherical cap of the sphere, of the surface of the sphere. Sphere. Okay, so we need to find a solid angle. One is the, what you should say, exact solid angle that we have derived, or we have like introduced the definition, and the other is just the approximation. So they say that your theta varies from 0 to 30 degrees, and your phi varies from 0 to 360 degrees. Okay, so first, the solid angle that we want to find is this. So as you know, that our solid angle will be sine theta d phi, from where your phi varies from 0 to 360 and your theta varies from 0 to 30. And if you just write it in terms of solid angle, you can also write it like that. Okay, like this. Okay, so we will solve this thing. So it's just very simple. It will become, yes, and so 0 to 30 degrees, and this will become, when you solve this thing, d phi. Okay, or should I not do it? Another thing you can do, you know how to change degrees to radian? Do you know that? I mean, can I write, if I want to write it in radian, can I write this as 0 to 2 pi and this as 0 to pi by 6? You know that, right? That's fine.
Yeah.
Okay, so I'm just trying to write it in radians.
Just one question.
Yes?
What happened with the 360 degrees? Or I guess 2 pi, like when you have the negative cosine theta.
Nothing, I'm just writing it.
Oh, okay. I'm sorry.
It's
Sorry about
okay. No, it's fine. Okay. Okay, yes, I can do that actually. So I can just write it like this. d theta, and it will become 2 pi and something like this, right? So what I did, I go from here to here, here to here, here to here, here to here. And then I can write this thing as, it's just, or I should not do this 30, it should be pi by 6. And I'm just writing it as minus cos pi by 6 and plus 1, right?
Yeah.
Yes, so the final answer I think they wrote is 0.83566, which is your solid angle. And we talk it in terms of radians, so just remember that it's not in terms of degrees. Okay? Now they are saying that the B part is that using the approximation, check what is the difference with the exact value. So their approximation was del phi 1 dot del phi 2, where they say that del phi is actually the theta that we are defining. So it should be pi by 3 multiplied by pi by 3, and it's pi squared by 9, which is 1.09, which is very much different than this one. So they said that it's almost 30% difference than this thing. So makes this thing less accurate, in which they do approximate angle in astronomy.
Was the pi over 3 given?
Yes, so they said that pi by 3 or approximate angle is this theta. Theta's maximum angle, that is pi by 3. Oh, not, oh, no. 1 minute. This pi by 6, right? Just a minute. What I'm saying. Yeah, it should be pi by 3. I was saying it's,
Did they just factor out like a pi over 3, like out of it? So
I mean, I don't know why they're
So it's
talking
not-
about Earth's North Pole, you know?
mhm.
It's just doesn't make sense to me. 1 minute. Okay, I'll come back to that. I was thinking that it's the same as pi by 6. Okay, I'll come back again, referring to Book of Astronomy, but this is fine. For our solid angle calculation is fine, and we may not use it again, this astronomy thing. Okay, but I'll come back to that, why they were saying pi by 3. Okay, but we know how to calculate solid angle, right? Is it fine?
Yeah.
Okay. So that's what the same thing we have done here. I think so, and we will come back to this one.
I think
Okay.
they literally just took it out of it. Like they just factored a pi over 3 out of a pi over 6. I think that's all they did. And then they like I don't know. Maybe I'm making no sense.
We will talk about it, but whatever they are talking about angular separation, I don't know. I mean, it's just so hard to learn about astronomy. I was looking at this yesterday and I was like, how they are checking the angles, but we will talk about it. Okay, so this is called sterads. Why? Because we took all angles in radians. Okay.
And if it's in degrees, what we would just write degrees, I guess, right? Okay.
Yeah, so this was degrees. This was degrees, and I converted into the radians. I just want to make sense with one thing. I think rest is easy. I just want to make sense. When I was student, I was always wondering from where our sine theta comes from. So our sine theta is nothing, but it's just the same as r day theta. It's just that you have this thing in terms of phi. Okay, so that's what here from it's come from in the solid angle. So are we clear about this? Because from now on, we will dig deeper into some more calculations, but I will try to touch basics where I will think that you may not know them. So it's just not that we will not start anything without knowing its basics, okay? So you just have to worry. Okay, so now I will go back to the lobes, major and minor lobes. Some people have the confusions about that, so we will just quickly touch upon that. We are clear about this? Okay. Okay, so see here, there was some confusion, I think what we were talking about here. Okay, and there was a confusion about first null beam width too. Just a minute. Okay, so when I was talking about lobes, I was saying that there are two types of beam widths, okay? One is first null beam width and the other is half power beam width. Okay, and if I try to see that, so if you see this one, so if this is my lobe, right? And this is my half power point. So in the field pattern, this is 0.707. And I was seeing that this is my half power beam width. And in the design block, we saw that we can find out the angles because it was on the polar plot. And in the polar plot, you can see that there are all the time angles. So if this is 120 and this is 60, so it will become 60 degrees of the half power beam width, right? But what is the first null beam width? So we were seeing that these were our lobes. So we said that these are side lobes. So this may be another lobe. So we were saying that these are the side lobes and this is our major lobe. And this is the side lobe. So we were saying, what is the first null beam width? So first null is, so there are multiple nulls here. So this is null. Null means where your energy suddenly becomes zero, okay? So that's called null. So here you have null, null, this is 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 null. So there are many nulls here, okay? So null is when your energy become zero, okay? So first null beam width is when you have first null and you try to measure the angle between them. So this is the first null after the major lobe, and this would be the first null beam width. Okay, is it clear? Saad, what do you think? Is it clear?
Yeah, it makes sense.
Okay. Any confusions? You good? Okay. So if I just go back then, there was a confusion, one more confusion we had last time about, I think, dBs. There was some point of dBs that we didn't take care. Okay. Okay. Not here. Here it was. Okay. So we were saying that ratio is often termed the side lobe ratio or side lobe level. Side lobe levels of minus 20 dB or smaller are usually not desirable in most applications, right? So what I anticipate is that if I say side lobe level, okay, if I say minus 20 and if I say minus 30, so for me, minus 30 is smaller than minus 20. Is it right? Right? Or is it greater? I just don't know. But what I meant to say that when side lobe levels should be small all the time, they should not be bigger. Okay. So it's maybe some tweaking of words, but low power of side lobe level is desirable. Okay. Not the high power. So if I'm saying that it's minus 30 dB, then it's good. If I'm saying it's minus 40 dB, then it's good. If I'm saying it's minus 15 dB or minus 10 dB, then it's not good. We just need to understand that. Otherwise, it's fine. Okay. I mean, maybe there is some contradiction in our understanding, but there should not be a contradiction that what we mean to say. We mean to say that side lobe levels should be suppressed. They should be smaller. Okay. Okay, so now let me quickly do this. Okay. So I am posting an interactive questions in your Canvas. So you can quickly access it and solve it, okay? So you can see chapter 2-1. Can you see that? On your Canvas, can you see that?
Yeah.
Okay, so I am just making random breakout rooms.
Sorry, where is it? And I only have chapter 1 still on mine.
It's
For
up
chapter 2.
below.
Chapter 2-1. In the files.
It's not. It's only in the files. It's not in the actual folder, Lewis.
Oh, okay. Thank you.
Yes, just the files. Chapter 2-1. So we good?
All good.
Okay.
Thank you.
So let's go and we will come back in 5 to 10 minutes, okay? You're ready? Okay. No, I don't want to be in any room. Just a minute. It's also placing me. It's placing me with Sarah, but I just don't want to recreate. Okay. And where am I? Okay, let's go.